To begin our presentation, I want to mention that threaded fasteners come in a wide variety of sizes, lengths, and thread forms, and are employed depending on the components made for. However, these fasteners require a threaded counterpart to screw into. And this is where we will focus our presentation because we find it very important to review that side of the process, especially since producing internal threads represents a higher difficulty level depending on the material the component is made of. As you might know, some holes are threaded using a tap or a thread milling cutter, which produces specific pitch diameters with a tolerance or a class of fit. Yes, there are other methods to produce an ID thread, but tapping and thread milling are the most productive ones. And this is what EMUGE-FRANKEN is well known for. Some safety critical component parts in aerospace are made of challenging materials that must held up to the demand of their environment or use. For example, safety critical component like landing gears must be made of super strong but light in weight metals like titanium alloys to support the heavy takeoff weight when the aircraft is full of fuel and the high impact load of landing. There are many, if not millions, of safety critical components in aerospace industry, also made of very difficult to machine materials. We are only showing you a few examples for the purpose of this presentation. As I stated above, fasteners are made of different lengths, sizes, or shapes depending on their use. But they need a threaded hole to assemble into. So here are some of the most common thread forms or profiles we see for fasteners in our industry. For the topic at hand, we have selected the 60-degree V-shape form as it is the most widely used form in most industries. And to be more specific, we will discuss two variations of this standard 60-degree V-shape form. One mainly created to limit microfractures at the crest of the threads in high vibration stress situations, and the other one developed to secure more clamping force of the fastened component, where the dynamic load is such that it causes the threads to come loose. The J-series threads and the EMUGE self-lock threads. We will begin with the J-series threads, but first, let's briefly review ID and OD threads, because these two forms, although both 60-degree V-shape, are not symmetrical. With that being said, it is worth mentioning that bolts are made to be of an exact mating value to a nut or a threaded hole of the same tolerance. Well, internal and external threads, although not symmetrical, they do have corresponding classes of fit for their respective pitch diameter tolerances. For example, the metric system uses a letter H or a small letter h for external threads and a big letter H for representing an internal thread tolerance value. In metric, the number in front of the letter goes in ascending order, like the larger the number, the bigger or looser the tolerance, and vice versa. In the UN imperial system, the larger the number, the tighter the tolerance. A bolt screw with a 2A free fitting class or 3A medium fit class will fit in an internal thread made to gauge 2B or 3B class in the UN system. The letter defines internal or external, A for OD and B for ID. Okay, let's talk about the J-series thread now. The J-series standard defines a system of threads for highly stressed applications requiring high fatigue strength. It was originally derived from a military specification MIL S8879, now inactive, and superseded by Aerospace specification AS8879. Due to the increase in
both its use and types of applications, the American Society of Mechanical Engineers developed and published ASME B1.15 standard in 1995, which covers these threads. For the purpose of explaining this system, I will use UNJ series. UNJC as well as UNJF refer to as a special thread type used in safety critical applications and commonly seen in aerospace industries. UNJ screw threads are of the same form as unified screw threads to ASME ANSI B1.1. It is different only in that there is a radius requirement in the root of the external thread. Because this is commonplace for stress fracturing to occur. The root has a maximum and a minimum prescribed continuous radius, and it is not merely rounded due to tool wear. There is no such requirement for the internal thread. However, minor diameter, controlled by the drill, by the way, is increased in order to accommodate the bolt. The minor diameter is increased to accommodate the maximum root radius of the external thread. That means that producing internal J-series threads will not be affected by which type we would recommend, although it is critical to make certain we are paying attention to our class of fit, with 3B being more common in this case. Many of the UNJ thread form characteristics are the same as for UN threads according to ASME ANSI B1.1. Therefore, a machine tab selected for producing a class 3B internal thread is suitable for a UNJ series thread. For this reason, we do not add a J to the shank marking of the tab as it is redundant and not required by the UNJ standard. The gauging of UNJ 3B threads is done in a manner agreed upon by the purchaser and the vendor. Basically, the same gauging system used in the checking of UN 3B thread and UNJ 3B thread are interchangeable, except for the minor diameter of the thread being larger on the UNJ thread, in light of UNJ threads being used in specific critical applications. The agreed upon gauging requirements may be more stringent from part to part. So for traceability purposes, we would have to have a special gauge produced for the exact call out of a UNJ. So let's do a quick comparison to illustrate this. You can see here, gauge limits are the same for UNF 3B thread as it is for UNJF 3B thread. We take this quarter 28 UNF and quarter 28 UNJF. First, see the difference in minor diameters. Do a quick recap and see what we offer. Internal UNJ threads are not required to have a root radius. Therefore, standard ground thread taps designated to produce unified screw threads of the proper class of fit may be used. The internal UNJ thread series is commonly designated a class 3B with an increased minor diameter controlled by the tap drill to accommodate the increased root radius of the external thread. When selecting a machine tab, the UNJ standard class of fit is 3B, unless otherwise stated on the part drawing, such as 3BG, which is oversized and requires special pitch diameter tabs. As you can see, we offer a wide range of tabs And we also offer a wide range of thread mills to meet these requirements. Especially with thread mills nowadays, which are made of mainly solid carbide with solid carbide edges, and by the nature of the interrupted cut process, we can use programming strategies to produce threads in difficult to machine materials like the ones found in aerospace. We have a wide range of thread milling cutters. We can also produce some modifications to standard thread milling cutters to meet the stringent requirements in this aerospace industry.
That brings us to the next part of the subject on producing threads in challenging safety critical aerospace parts. Let me start by mentioning we produce threads and use fasteners to hold components in place. However, even the highest quality screw, nut, or bolt can come loose unexpectedly, often at the worst possible time, when subjected to vibration or other forces. That's because threaded fasteners are intended to come apart. It is an unfortunate truth, or a fortunate one depending on your perspective, that all machinery and other mechanical assemblies must be constructed in a manner that allows them to be serviced, refilled, or repaired. If not, they could simply be welded together, eliminating the need for threads entirely. There have been several ways manufacturers have tried to secure threaded fasteners. One common approach is with a pair of washers, one flat, the other split, known as a spring or lock washer. Unfortunately, this arrangement is not failure-proof. As many manufacturers have found, vibration and dynamic loading tend to loosen even the most tightly torqued screw, lock washer or no. Some recommend applying a liquid adhesive or a dry patch to the threads during assembly to prevent loosening, which is why any mechanic is familiar with using Loctite and other commercially available adhesives, and so on. And I am sure you probably know of more. But that brings us to one of the more successful attempts to secure fastener. It involves modifying the conventional 60-degree form by cutting a locking ramp on the internal thread, securely and predictably locking the fastener in place while making it easy to assemble and disassemble multiple times. As you'll see, it was a great idea, but one that was poorly implemented, at least initially. In 1979, the Detroit Tool Company made a simple modification to a standard thread profile. They called it spiral lock, and it soon became quite popular for use in mission-critical applications by the military and aerospace manufacturers, and eventually the medical industry. Unfortunately, no ANSI or ASME or DIN standards exist for the wedge ramp design. Many in the manufacturing industry adopted a proprietary thread form, and when the patent ran out in 1994, the Detroit Tool Company sold the spiral lock name to Stanley Engineered Products, a well-known manufacturer and distributor of threaded fasteners, rivets, washers, and other hardware items. Since that time, the wedge ramp thread form has continued to gain popularity, and for good reasons. Unfortunately, manufacturers choosing to adopt it have long been locked into a single supplier, one that does not manufacture cutting tools, but instead sells them to its customers on a private label basis. EMUGE-FRANKEN recognized this situation and soon obtained the rights to manufacture taps, thread mills, and inspection gauges for the wedge ramp form, but were not allowed to do so under the spiral lock trademark name. Because of this, the cutting tool manufacturer was forced to file its own trademark, self-lock,
and began producing tools and gauges at its plant in Germany. With a conventional 60-degree thread form, the mating components make contact along their respective thread flanks. Unfortunately, this creates a small amount of radial clearance between the fastener's major diameter and that of the threaded hole. When subjected to vibration, this clearance allows just enough transverse motion for the fasteners to gradually loosen. The EMUGE self-lock feature is integrated into the internal profile and works without any additional mechanical or chemical locking devices. Therefore, temperature or vibration do not noticeably affect it. The wedge ramp design prevents any transverse movement, thereby locking the fastener securely in place while also making the thread much stronger. The study shows that where a traditional tapped or thread mill hole concentrates as much as 75% of the load on the first two threads, one with the wedge lock design carries the load evenly along the entire thread's length. A modification to the standard thread profile form of a 30-degree wedge ramp surface on the major diameter produces a locking effect since the bolt thread is not affected in any way. Standard bolts of tolerance class 2A or 6G can be used. Once again, a self-lock threaded hole is made with a 30-degree ramp or wedge form adjacent to the thread's root and oriented perpendicular to the direction of stress. This wedge surface engages with the crest located at the fastener's major diameter. As the screw is tightened, it forms a continuous and concentrated point of contact along the entire thread length. So, although spiral lock and EMUGE self-lock concepts are identical in thread form and function, they are not interchangeable. This is due to some slight dimensional differences, but it means that manufacturers need to select the correct gauges when producing and measuring these threads, and must decide on one brand or the other. And so, as I mentioned earlier, there are no standards for locking wedge ramp style thread forms. Because of this, OEMs who specify these forms in their product's design should first confirm that their in-house machine shop and tier supplier have a comprehensive, well-supported platform for producing these threads. At the top of the list for this platform are high-quality, readily available, and cost-effective taps and thread mills. The supplier should also offer a broad assortment of these cutting tools with the geometries and the coatings needed to tackle different materials productively. In addition, machine shops need precision gauges with which to measure threaded holes during production. And even though neither ANSI, ASME, nor DIN standards exist for wedge ramp fasteners, these gauges should be traceable to a known ambiguous source. The EMUGE self-lock gauges, as well as all of the other thread gauges, are certified by in-house gauge certification laboratory. As you can see, EMUGE-FRANKEN checks all of the points mentioned. We have also been manufacturing cutting tools for more than a century now, starting with the invention of the world's first spiral point tap. Please feel free to check out this particular self-lock brochure on our website. And now I'm going to tell you more about a specific tool. So the one tool I would like to highlight for you in this presentation is the EMUGE ZGF S-Cut thread mill. This helical flute multi-tooth cutter has a 10-degree left-hand helix requiring a left-hand spindle rotation, which greatly enhances stability and performance. 3-teeth design, first tooth acts as a rougher, second and third tooth finish the full profile, increasing tool life and reducing cycle time. It has a TILN T46 coating, which resists heat and wear, extending tool life also. Internal coolant starting at sizes 1/4 inch and above. With this family of tools, we are able to combine a tool geometry with a programming strategy to create a very stable thread milling process with a very innovative cutting edge technology. We offer it in metric and UNC and UNF, and we also offer it in self-lock profile. The main thing to keep in mind about these tools is to use a left-hand spindle rotation for the 10-degree left-hand helix on them. So how does it work? Well, first you have to know that there are two separate directions you can mill any surface, a climb or a conventional direction. Each has its advantages and disadvantages. But what if we could make it only the advantages of both methods and create the tool known as the most stable thread milling technology in the market? So with climb milling, you get a nice comma-shaped chip decreasing in thickness from thick to thin. You have better tool life, and it's very quiet running. However, the disadvantages is that there is a lot of free play and high stability of the machine clamping is required. Conventional milling, however, works best in hard materials, castings, forgings. The disadvantage is that it's inclined to chatter or heavy sound pitch and harmonics. So what we did with the ZGFS cut is we combined both of these into one. Since we are rotating the spindle to the left and we are entering the part in a conventional milling routine, meaning we come in from the outside in so that we can take advantage of the roughing tooth on this tool, we are already thinning the chip and creating a lot more stability, especially for the really difficult materials like the ones we see in the aerospace industry.